as I was telling you in my previous lecture, the postulate 3 says that if you have an observable and if you make a measurement of that observable, the answer will be an eigenvalue of the operator that is associated with the observable. Now, observables, whenever we make a measurement, we will have to get real numbers, right. But this postulate says that those numbers are eigenvalues of the associated operator. So, therefore, it is a must that the eigenvalue of the operator must be a real number, right. And in our previous postulate, we said that operators are Hermitian. So, the reason for saying that these operators are Hermitian is that it is possible to prove rigorously that Hermitian operators have always real eigenvalues. Okay. So, that is the reason why the word Hermitian occurs in the previous postulate, and in fact, when we proceed sometime during the course, I will prove that Hermitian operators have always eigenvalues which are real. All eigenvalues of a Hermitian operator can be proven rigorously to be real. So, if you think of the Hamiltonian operator for the harmonic oscillator, we saw that the expression for it is given by minus h cross square by 2m dou square upon dou x square. This comes from the kinetic energy of the particle, and then in addition to that we have the potential energy occurring in the Hamiltonian operator, and for a harmonic oscillator the potential energy is actually given by 1 by 2 k x square, where k is known as the force constant for the harmonic oscillator. I give you a physical example. This is a hydrogen atom attached on the surface of tungsten, and the bond between the hydrogen and the tungsten may be thought of as a spring with a force constant k. Now, what do I mean by that? It means that you see, if you displace this hydrogen atom from its equilibrium position by a distance x to a new position by a distance x, then the bond is going to be stretched and there will be a force trying to restore it back to the equilibrium position, and the restoring force actually will be proportional to x, and the force is actually equal to k times, its magnitude is equal to k times x. That is the meaning of saying that the force constant is k. And because you see it is in the direction that is opposite to the direction in which x is increasing, we say that the force is actually minus kx, because it is in the opposite direction to the direction in which x is increasing. And actually, if you study the classical mechanics of this, which we will not discuss, what will happen is that if you displace this atom and release it, it will execute oscillations, it will execute harmonic oscillations, and it will execute a given number of vibrations per unit time, and the number of vibrations is usually denoted by the symbol nu, and it is obviously going to depend upon how strong this bond is and how heavy this atom is. So, therefore, you can expect the dependence of this frequency vibration on the mass of the atom as well as on the force constant, and in fact, if you study the classical mechanics of the system, you will find the information that it executes a given number of oscillations per unit time, given number of vibrations per unit time, referred to as the frequency of the oscillator, and frequency is related to the force constant and the mass of the particle by this relationship. So, this is the number of oscillations that it will execute. Now, quantum mechanically, suppose you have such a system and you are able to measure its energy. What this postulate says is that the answer is going to be an eigenvalue of this operator h. So, therefore, you want to know what the eigenvalues of this operator are. because if you make a measurement of energy, the answer is going to be a particular eigenvalue of this operator. So, how do you find an eigenvalue? The answer is that you will have to allow H to operate upon some function, maybe phi, such that what will happen? I am going to say phi is an eigen function of this operator. So, what is going to happen is that I am going to get phi back, but multiplied by a constant, multiplied by an eigenvalue, and that eigenvalue I need a notation for it, but this eigenvalue is eventually going to be the energy of the system, right, because of the postlet. So, therefore, what I will do is I will denote this by maybe some symbol which I may denote as epsilon. Okay. So, if you make a measurement of energy, then what is going to happen is that it is going to be an eigenvalue of the operator. So, if epsilon is an eigenvalue, then the answer could be that epsilon. In fact, in the case of the harmonic oscillator, with this Hamiltonian operator, you can actually find the eigenvalues as well as eigenfunctions, something that we will do later. So, it is possible to show that the eigenvalues of the harmonic oscillator have the form which I am going to write. They are of the form n plus half h nu. As I told you, it is possible for an operator to have several different eigenfunctions, each having its own eigenvalue. So, therefore, if you ask me a question like how many eigenvalues can an operator have, normally the answer will be an infinite number of eigenvalues. So, this particular operator has an infinite number of eigenvalues, and they are of the form n plus half h nu, where n is a number characterizing the eigenvalue, which can take the value 0, 1, 2, 3, 4, etc. This means that the different possible eigenvalues are obtained by putting these values of n, which are actually half h nu if you put n equal to 0, or 3 by 2 h nu, or 5 by 2 h nu, etc. These are all different possible eigenvalues of this Hamiltonian operator for the harmonic oscillator. So, what it means is that if I can measure the energy of the harmonic oscillator, then the answer that I find will be one of these eigenvalues, and you are not going to get any other answer. That is what this postulate says. One of the eigenvalues, maybe it may be half h nu, or maybe it will be 3 by 2 h nu, or maybe it can be 5 by 2 h nu, and so on. So, the answer is guaranteed according to this postulate to be one of these different eigenvalues. Similarly, if you are making a measurement of position, what will happen is that it has to be, the answer has to be an eigenvalue of the operator that is associated with position. Or if you think of making a measurement of momentum, the answer has to be an eigenvalue of the momentum operator, right. But then suppose I make a series of measurements. I have this harmonic oscillator which is vibrating, and I am going to measure its energy again and again and again at different instants of time. I make a measurement now, maybe I will come back tomorrow and again make a measurement, maybe next day I will make one more measurement, and so on. So, I make a series of measurements. Okay. Now, it is not guaranteed that I should get the same answer. This is one peculiarity of quantum mechanics that I have already spoken about, right, in my previous lectures. It is not necessary that I should get the same answer. So, imagine, I will make a very general statement. Imagine that I have an operator A which is associated with some particular observable, and this has different eigenvalues. First eigenvalue is A1, second is A2, third is A3, etc. There are so many eigenvalues, and what am I going to do? I am going to make a large number of measurements. Okay. Now, the first time I make a measurement, maybe I will get the answer A1, second time it may be A2, it does not have to be the same. So, let us say I make a large number of measurements, and what happens is that I shall get, let me say n1 times I will get the answer A1, n2 times I get the answer A2, n3 times I get the answer A3 and so on. So, in given such a situation, what you do, you will make the average of all these numbers that you get. So, how will you define the average? It is going to be n1 A1 plus n2 A2 plus etcetera until, I mean, it goes on, divided by the total number of measurements, right. The total number of measurements is n1 plus n2 plus n3 etcetera. So, therefore, this will be the average value of my observable. So, I will say that the average value of all the measurements that I have made is equal to so much. Okay. Now, see, if you wanted to find this average, actually it is not necessary to make the measurement. It is possible to calculate this average from quantum mechanics, right. So, therefore, if you want, you can calculate the average from quantum mechanics, then make this is the experimental measurement and find the average, and then the two are going to match. That is what this postulate is going to say. So, let me continue this postulate and say that the average of a large number of measurements, this average, I have given you the experimental definition of average. What is it? You make a large number of measurements, the first eigenvalue you get n1 times, second eigenvalue you get n2 times and so on, and then you calculate the average. If you want, you do not have to make the measurement, you can just get the average value by doing a calculation. What is the calculation that you have to perform? You take the state function for the system, which, as you know, we will denote by psi, allow the operator to operate on it, and then multiply the result by the complex conjugate of psi. Let me repeat, I take the state function, this is, I know that my system is in a particular state and the state function psi I know. If I know that, then I can allow A to operate upon it, multiply the result by complex conjugate of the state function, then the volume element d2, and then integrate over the entire space. I will get some number as the answer. And so, you calculate this number and divide this by integral of d2 psi star psi. Okay. This is the experimentally measured average, that is what this postulate says. Okay. Now, you may wonder, I mean, if you think of psi star psi d2 integrated over the entire space, you see, if your wave function is normalized, then this is guaranteed, that part is guaranteed to be equal to 1. So, this expression is valid even if the wave function is not normalized. If in the case, special case where the wave function is normalized, this is actually going to be equal to 1. And this object in quantum mechanics, it is actually usual to denote this itself by the symbol A with that kind of brackets on both the sides, and it is referred to as the expectation value of A. Expectation value of the operator A. This object is referred to as the expectation value of the operator A. So, what this says is that, you see, if you wanted to find the average of a large number of experimental measurements, all that you need to do is just calculate the expectation value of A using your state function, that is enough, that will give you the average of a large number of measurements. Okay, there are a few things that can be proved from here, but I am not going to prove all of them, but what I want to say is something which is very important. Suppose it so happens that your state function is an eigen function of A. suppose it so happens that your state function is an eigenfunction of A, right, and let me say that small a is the corresponding eigenvalue, small a. So, therefore, A operating upon psi is going to give me small a times psi. Then what will happen? Think about it, right. You will have small a times psi. So, maybe I can do it here. This may be replaced with small a times psi, and A after all is just a constant. It will not be affected by these integrations that you are going to have. So, this small a can be shifted from there and you can put it here, right, and then you will see that the numerator and the denominator are having common factors. So, you can remove this, right, and therefore, what is it that you find? If the answer is very simple, the answer is that if your state function is an eigenfunction of the operator with an eigenvalue A, then the expectation value is actually nothing but the eigenvalue. Okay. So, this says that if you make a large number of measurements, the answer is going to be that particular eigenvalue, right. That is what this says. In fact, I have just proved that that is the way it is. But then in addition, you can prove, this is something that I will not prove, that you can go on measuring a large number of measurements. In this special case where psi is an eigenfunction of A, the answer will always be that eigenvalue. See, what I am saying is something stronger. Earlier I said when I make a measurement, it is not necessary that the answer should be the same, but in the case where the state function is an eigenfunction of the operator that you are measuring, then the answer will always be the same and it will be equal to the same eigenvalue. I have not proved it, but it is possible to prove that. So, therefore, I mean if you want to illustrate, if you want an illustration, imagine you think of this harmonic oscillator. Imagine that it is in a state which is an eigenfunction with, it is an eigenfunction of H, suppose it is the state function is an eigenfunction of H corresponding to maybe this particular eigenvalue phi by 2 h nu. Then you can make the measurement of energy any number of times, answer will always be phi by 2 h nu. And if the answer is always phi by 2 h nu, what about the average? Average also will be phi by 2 h nu. Okay. So, that is what this means. Now, you see this particular postulate has been a subject of many large amount of controversy, because people were very unhappy about it. They tried all kinds of things with this postulate, and it is a postulate in which research is being done even now. And the subject of this postulate comprises what is referred to as measurement theory and quantum mechanics. Okay. And in the last 10 years or so, there has been so much progress, and if you are interested, you should have a look at this particular website. And you will find that this website has discussions of what is referred to as decoherence. I hope you can see this. Decoherence, this is concerned with measurement theory essentially. As I said, a lot of research is being done even now on this particular postulate or the subject matter of this postulate. So, if you remember, you see in the first postulate I said that the state of the system is characterized by its state function, right, and if you know the state function, it is possible to calculate the probability of that the system may be in any region of space. That is what the first postulate said. In the second postulate said that if you have an observable, then there is an operator associated with it, and that operator has to be linear, it has to be Hermitian. Then we also had a prescription for finding the operator. Then in the third postulate, which we have just discussed, it said that if you make a measurement, the answer is guaranteed to be an eigen value of the operator associated with the observable that you are measuring. But you see, I mean, you would realize that knowing the state function is extremely useful, but we do not have any procedure for finding this state function, and that is the subject of the next postulate, which is postulate number 4, the final postulate. So, this is the postulate. It says that the state function obeys the time dependent Schrodinger equation. As I have mentioned earlier, see, we have these 4 postulates, but instead of that I could have actually started with this path integral approach, introduced that path integral formula that I had as a postulate, and then try to derive quantum mechanics therefrom. And if you did that, you see, starting from the path integral formula, it is possible to derive this equation. If you assumed that, it is possible to derive this particular equation, which is written here. This equation I have to explain a little bit more, I will do that. Or if you want, you can assume this particular equation, and derive the path integral formula that I had written in my earlier lectures. Okay. So, this equation, let me illustrate it by writing it maybe for a simple one dimensional system. So, imagine I have a one dimensional system. I mean, as I always do, I think of illustrating whatever equations that we have in the simplest possible case, which is a one dimensional system. So, you have a one dimensional particle moving along a direction, and its position is specified by x. So, naturally the state function psi will be a function of x and the time t. That is how it is. That is what the first postulate says, and we want to determine the state function. And how can I do that? The answer is that I have to worry about this equation, which says that I h cross dou by dou t operating upon psi. In this particular case, psi is a function of x and t, just 2 variables, because it is a one dimensional system, and that must be equal to h. What is h? Well, h will contain 2 terms, one coming from the kinetic energy of the particle, an operator coming from the kinetic energy of the particle, which we know is minus h cross square by 2m. Not just that, because you will have 2 differentiations with respect to x. So, this is the kinetic energy part of the Hamiltonian operator, and then in addition to that, if you denote the potential energy of the particle by the symbol V, okay, in general V will depend upon x, and maybe it can change with time, in which case it is a function of both x and t. If you have a potential which changes with time, then it will be V of x t, and this is your total energy, or the operator associated with total energy, and what will happen is that this is going to operate upon psi x t. So, this is the equation. So, what has been written in this form is rewritten on the board for a simple one dimensional system. And if you are interested in knowing the state function, what you have to do is you have to solve this equation, right. If you are able to solve this equation, you are going to get the state function. Now, for a more complex system, this equation will be more complex naturally, right. If you had, let us say, helium atom in this room which was moving about in this room, what is going to happen is that you are going to have this equation I h cross dou by dou t, correct. Now operating upon what? You will have a psi which is a function of x, y and z, because you are thinking of a 3-dimensional system. So, you will have x, y, z and t, and that is going to be equal to minus h cross square by 2m, because your particle is moving in 3 directions. You will not have just dou square upon dou x square, but you will have dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square. I mean, that sum, if you remember, is something that we decided to denote by del square. As I always say, I am lazy, I do not want to do the work of writing dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square. So, I just write del square. Now, if you had included the gravitational energy, then what will happen? You will actually have a potential energy there which will be of the form mg z. If you decide to include the gravitational energy, but normally it is not important, so we are not going to do that. This will be the equation which will determine the state function. If you had included the gravitational energy also, but if you do not include it, this term will not be there. The gravitational potential energy, I mean, as I said, it is not of any importance for most of the problems, and so it is not necessary to worry about it. So, this will be how the equation looks like, and if you look at this, you again see what it says is that, you see, as time passes your state function is going to change. That is what this equation says, and the derivative of the state function with respect to time is determined by what? It is determined by the state function itself, but operated upon by the Hamiltonian operator. So, the Hamiltonian operator determines how the state function evolves in time. How the state function changes in time is determined by the state function itself, operated upon by the Hamiltonian operator. So, the time evolution or time development of a quantum mechanical system is governed by what? It is governed by the Hamiltonian operator, and that is the reason why Hamiltonian operator is of great importance in quantum mechanics, because it determines how the state function changes with time. Okay. Okay, we have had enough of the postulates, and we are now going to look at some consequences of these postulates. Okay, let me tell you the most important consequence of these postulates. Okay. Remember, earlier I was speaking about standing waves, remember, and I said that if I had a system in which there are waves, then it is possible for the waves to form a standing wave, right. So, you would expect that kind of thing to happen in quantum mechanics, because everything is actually determined by waves. So, what we want to look for are actually the analogues of these standing wave patterns, and these analogues are actually referred to as stationary states in quantum mechanics. Okay. So, what we will actually rigorously show is that if you have a situation where the potential energy does not change with time, right. Here if you look at the equation, the way this equation is written, we can be a function of time, but imagine that you have a situation where the potential energy does not change with time. Okay. Then it is possible to show that there can be states which are referred to as stationary states. Okay, maybe I can illustrate this better. See, this is a pictorial representation that I have adopted, something that is wavy. This, let me say, is the wave function, and what this equation says is that as time passes, this wave function is going to change, right? That is what it means. So, suppose as time passes, what will happen? You see, your state function is going to change, and that change I have just indicated by drawing some lines. And what happens? You see, this is my state function at an initial time, this is after some time. So, you can see that the shape of this wave function has changed in general. This is what happens in general, but there are certain special situations where what happens is that even though the system evolves in time, the shape does not change. Okay. So, those are the states that we are referred to as stationary states, and we want to find them. And the question is, how do we find them? So, in general, as Professor Calculus says, in general the state function actually changes, but it is possible to think of special situations where even though the time is passing, the shape of the wave function does not change. So, how does one find that? The answer is the following. First of all, we imagine that the potential energy does not change with time. That means, in this equation, I mean, we will think of a one dimensional system, but whatever proof I am going to give you can be generalized very easily to any number of dimensions, whether it is 3 dimensional or a bigger dimensional system. So, whatever proof I am going to give you is generally applicable. The only condition is that the potential energy should not depend upon time. So, suppose the potential energy does not depend on time, then what will happen? There is no time there. And you want to solve this equation. So, how do you solve this equation? Well, if you look at this equation, you will realize that it is a partial differential equation. There is a partial differentiation with respect to time, here partial differentiation with respect to position. So, you want to solve this equation, and even ordinary differential equations can be difficult to solve. So, in such a situation, how do you find solutions? Well, what we adopt is a method of divide and conquer. So, this psi, which is a function of x and t, imagine that we have a solution which is of the form psi of x into capital T of t. See, what we are saying is this: capital psi is a function of x and t, but now I am going to say, okay, let me think of only those cases where capital psi can be written as a product of two functions. The first one I will call small psi, the symbol, the way, look at the way it is written, this is capital psi and that is small psi, and small psi I will assume that it depends only upon x. And then there is another function here which I will denote by the symbol capital T, and that I am going to say will depend only upon the time t. So, I have split my total wave function, which actually depends upon x and t, into two separate parts. So, I have divided it into two separate parts. The first part depends only upon x, the other depends only upon the time t, right. Now, obviously, you see this will not happen in general. So, this is something special. This assumption, it will not have general validity. So, we are actually finding some special solutions of the equation for which this kind of separation can be done, right. So, then the question is, I want to adjust small psi and capital T, that means I want to choose small psi and capital T in such a fashion that the product will obey this equation, that is what I want to do. Okay. I want to choose small psi and capital T in such a fashion that the product will obey this equation. So, let us see what happens if I took this assumption. This is actually an assumption. I take this assumption and put it back into the original equation which I want to be satisfied. So, if you do that, you are going to get I H cross dou by dou t operating upon capital psi, but capital I have assumed is given by this expression. So, psi of x capital T of t is equal to minus h cross square by 2m dou square upon dou x square plus v of x operating upon psi of x capital T of t, right. This is what happens if you took this assumption and put it back into the original equation. But then if you look at the left hand side of this equation, you have partial differentiation with respect to t. Now, when you are partially differentiating with respect to t, that means you are not allowing x to change. So, as far as this differentiation is concerned, psi of x is a constant. So, it is not affected. So, this partial derivative is going to affect only capital T. So, therefore, I can write this as I h cross psi of x dou by dou t operating upon capital T of t, and that is equal to the right hand side. On the right hand side, you have partial differentiation with respect to x. So, this is going to affect only psi, it is not going to affect capital T. So, this capital T is completely unaffected by whatever is there in this operator, because there is no time anywhere in this operator. So, you can take this capital T of t outside, and then you will have minus h cross square by 2m dou square upon dou x square plus v of x operating upon psi of x. Okay. Now, I am going to rewrite this in the next step. Before I rewrite, what I want to do is I want to divide throughout by psi of x into capital T of t. Suppose I divide throughout by this, then what is going to happen is you will have I h cross divided by psi of x into capital T of t dou capital T by dou t is equal to, well, I have made a mistake, there should have been a psi of x here, and on the right hand side you are going to get capital T of t divided by psi of x into capital T of t, then minus h cross square by 2m dou square upon dou x square plus v of x operating upon psi of x. And it is obvious that you can cancel this psi with that psi and that capital T with that capital T. Well, in order to make the equation look neater, what I will do is I will rub off these things, and the same thing here. So, this is the result. And if you look at this equation, what do you find? You find something that is very interesting. See, this was a partial differential equation which depended upon two variables, t as well as x. These both t and x, they are independent of each other, they are independent variables of the problem. But when you look at this equation, you on the left hand side you have a function which depends only upon time, a function of time alone. So, maybe some function of time. What about the right hand side? This whole thing, you see that it depends only upon x, it depends only upon position. So, this equation is actually of the form f a function of time is equal to a function of x. How can that be satisfied? Well, it is very easy to argue that such an equation implies that both of them have to be equal to the same constant. Okay. Let me argue that, I mean in general at the most what may happen is that you see both of them may be equal to some function which I may denote as lambda, which may depend upon x and t, that is all. At the most what may happen is that both of them will be equal to something which may depend upon x and t, but then this lambda, you see if you look at this, lambda is equal to a function of time alone. So, therefore, it cannot depend upon x, correct. This lambda is equal to it. At the most what can happen is that both of them may be equal to some function of x and t, because x and t are the variables that you have in your problem, but lambda is equal to a function of t alone. So, therefore, it cannot depend upon x, and lambda is equal to a function of x alone. So, therefore, it cannot depend upon t, and therefore, lambda has to be a constant. That is the way you can argue. So, therefore, if such an equation is to be satisfied, f of t must be equal to a constant. Okay, for certain reasons I will call that constant E. I mean you could have used any symbol, but you will see that eventually it is connected with the energy, it is actually the energy itself. That is the reason why I prefer to use the symbol E, but at the moment it is just a constant, and this constant does not depend upon either time or position, right. So, what has happened is that I have got an equation which reads IH cross divided by capital T of t dou capital T by dou t is equal to E. That is one equation that I have obtained, correct, and I have obtained another equation. Let me just as I said, I am somewhat lazy, I do not want to write things again and again. So, I will just say that this is equal to E. So, these are the two equations that I get, and if you look at these equations you would realize the first is actually an ordinary differential equation. What about the second? The second also is an ordinary differential equation. The first equation involves only the variable time. The second equation involves only the variable position, right. So, your original equation, remember, was this. The original equation was a partial differential equation, involved both the variables, and as I said, the partial differential equations are difficult to solve. But what we have done is we have divided the function into two parts, psi of x and capital T of t, right, and separated out two ordinary differential equations. So, one is this and the other is that, and ordinary differential equations obviously are easier to solve than partial differential equations. And now we can go ahead and try to solve these two equations, and if I solve these two equations and determine the values of psi and capital T, then what I can do is I can use those values in here and get the total wave function, right. This method is known as the method of separation of variables. So, what do I mean by that? The meaning is I had a function which depended upon two variables and that I separated into two separate functions, each one depending only upon one variable, right. And then I was able to arrive at two separate ordinary differential equations. So, one is this and the other one is that. So, my problem has been simplified by this method of separation of variables. Now, a crucial thing to notice is, would it have been possible if V depended upon x and time? See, if V depended upon x and time, suppose you had t here, what will happen is that you will have t sitting here in this equation, correct? You will have a t sitting there, and the argument of this method of separation of variables will not hold good. You will not be able to separate the variables, and therefore, you see, if your potential energy depended on time, you will not be able to find a solution, a simple solution of this form, and the method of separation of variables will fail. Okay. So, this argument can be carried out only in those cases where the potential energy does not change with time. But then you may ask, are there problems where the potential energy is changing with time? The answer is yes. If you are interested in spectroscopy, for example, imagine I have a molecule here and I shine light, maybe the tube light acts on the molecule, right. The electric field from the tube light can act on the molecule. As you know, the electric field in light will be oscillating, it will be changing as a function of time. I mean, the electric field is actually changing. So, effectively, if you had a molecule and if you subject it to light, there is an electric field which change time dependent electric field, an oscillating electric field acting on the molecule, and the molecule is made up of charges, electrons and nuclei, and so this electric field will affect these charges. So, the moment you say, okay, there is interaction of the molecule with electromagnetic radiation, your potential energy will become a function of time, right. So, if you are doing spectroscopy, this method will not be, I mean, the procedure that we have adopted will not be valid, you will have to modify it. Okay. Well, we will continue in the next lecture.